Okay, so good morning, everyone. Today we have Joe Jansen. He is a PhD student at the University of British Columbia, and he will be discussing full identification of linear additive noise, SDEs, for temporal snapshots. So welcome, Joe, and the floor is all yours.
Yeah, thanks, Lila. So today, it's going to be a bit of a different topic than usual, but I promise you there's some geoscience in here and also some information theory, so we'll get to that eventually. But, this topic is maybe going to be new to some of you, so just feel free to stop me whenever, and I can explain further. So this is a paper. I'm going to be presenting on a paper that myself and a bunch of my colleagues in the math department are working on. And we should have a preprint out like, I don't know, 2 or 3 weeks, or definitely within November, but hopefully before then. So the topic of the talk will just be about stochastic differential equations. So you might have heard of these things being used for applications in like gene regulatory networks, or like particles or contaminants flowing through some medium, or also modeling stocks on the stock market. And the basic components of the SDE, we'll call it, are shown in this middle equation here. So we have this incremental change in xt is given by bxt, which we'll call the drift or the advection term, dt, plus the sigma x of t dwt. So this last term here is called a diffusion with the sigma xt, and this dwt is basically increments of what's called Brownian motion, or Wiener processes. So most of the SDEs that are studied, and most of the stuff we'll be talking about today, are of the form of this linear additive noise SDE. So you replace this BXT with a matrix A, and you replace this sigma XT with this matrix G. So these, this noise term G dWt is basically normally distributed with mean zero and covariance G gt dt. So the main problem that we're focusing on in this paper is for parameter estimation. And the reason why is because parameter estimation gives you basically everything else we would want. So we'll see later in the talk that it basically gives you the full causal graph, which is great. It gives you trajectory inference. So if you want to know where a particular contaminant particle ends up somewhere down the line at time t equals 1,000 or whatever, it can tell you that. And it also can give you these post-interventional distributions, which is basically if you kind of intervene on one of your variables, what happens to the rest of the system. So again, our goal is to recover this drift matrix A and this diffusion H, which is G GT. A good thing to note is we can't actually recover G. The only thing that we can hope to get is this H term. So the thing about estimating these parameters is that it would be very simple if we could have like time series of our processes, but oftentimes that's not the case. So like the main example I'll talk about with you guys is this contaminant transport problem, where we can't really track individual particles through time, but we can understand kind of the distribution of these contaminant plumes, or some tracer going through some medium. And in the SDE literature, and basically mostly in this gene regulatory context, these are called marginal or temporal snapshots. So you can imagine pausing this GIF at a particular time point and taking that data of that distribution, and we call that the snapshot or the marginal. And we can sample that at a couple different times, and then hopefully we can actually recover the parameters driving these individual contaminant particles in the system, even though we don't observe them directly. So again, we're going to be dealing mainly with this linear additive noise SDE on the top here. And what we observe are these marginals, these PXT. And in the hydrology literature, this is usually denoted by C, which is the concentration of some tracer or particle. And this is given by the way in which this marginal changes with time is given by what's called the Fokker-Planck equation, which is listed here. So you can see this probability distribution is changing with A, which is the drift, and also H/2, which is the diffusion. But what we want to know is, like, is this always possible? It's not clear that from these marginal snapshots that we can actually recover what we want, which is A and H. So we want to kind of look at the non-identifiability in the math terms and equifinality in hydrology terms of these parameters. So is there more than one parameter set, A and H, that can explain these marginal snapshots? And it turns out there are. So a lot of people have brought up, so we're going to go over 3 examples of non-identifiability or equifinality, which a bunch of people have brought up in the past. So the first one is where you kind of start at your stationary distribution. So it turns out if your initial marginal that you observe is already in the stationary distribution, you can have totally different processes. You can see on the left here, the time series, which again we don't observe, are totally different. The top one is barely changing at all, but the bottom one is really noisy. It's going crazy all over the place. But actually, if you look on the right-hand side, the marginal distributions over time of these two processes are the same. And that's basically because they have the same kind of drift diffusivity ratio. So this 10 versus square root of 10 and 0.1 versus square root of 0.1. Another example of non-identifiability is this rotation example. So on the left-hand side, we just have kind of a circular Gaussian isotropic, kind of a ballooning up in time. And the other one, on the right-hand side, we have a Gaussian that's kind of ballooning, but also rotating. And because it's, basically circular, you can't really tell the difference between the two processes. And the final example is about rank degeneracy. So in this case, the drift field and the diffusion field are doing different things outside of this kind of 1 minus 1 line. But inside this line, they're exactly the same. So you have even though the drift and diffusion are different for both these processes, we have basically the same processes going on within this kind of null space of the vector field. So I just gave you 3 examples of where we would see some equifinality when we're trying to identify these parameters, but we want to know, are there some general conditions that we can find where we can actually uniquely identify these parameters and get what we want? So once we have the parameters, we can get the causal graph, trajectories, and also these post-interventional distributions. And it turns out the identifiability conditions are quite general. So it actually has to do basically with these rotations. So first we'll kind of go through these a little bit of preliminary, and then I'll kind of wrap it up with the conclusion. So we call kind of these circular distributions as rotationally invariant, but you can also have these ellipses, which are also rotationally invariant, but in a more general sense with respect to kind of their geometry. So we call the circular one kind of rotationally invariant, and then the elliptical distributions we call sigma generalized rotation. So it's kind of rotating with respect to its kind of covariance sigma. And you can kind of see this here. So we call this autorotationally invariant if if we can kind of find an A that's non-zero that makes e to the at x the same distribution as x. So basically the rotation matrix e to the at is not changing the distribution of x. And it turns out this class of distributions that are autorotationally invariant is quite small. So if you have like a rank degenerate distribution, like a 2 Diracs in 3-dimensional space, then it's autorotationally invariant, and also Gaussians. But there's not many more cases where we see this autorotationally invariant kind of distributions. Yeah, so these are kind of more general examples of our first examples where we show kind of how this autorotationally invariant thing leads to non-identifiability. So these kind of elliptical distributions are actually, well, one is not rotating and the other is rotating, but you actually can't tell the difference because it's rotating with respect to its covariance, basically. And kind of similar with this, I guess. So it turns out if x naught is not autorotationally invariant, so basically not Gaussian and a couple other cases, but basically in all cases, we can actually identify both the drift A and the diffusion GT, which is great. And we prove this in the paper. And also, oh, sorry. Yeah. So if we start out with our initial distribution, our initial marginal x naught as something that's not autorotationally invariant, we can actually revisit some of our non-identifiable examples and see that they become identifiable. So this is the first case where we had this 0.1 drift versus 10 drift looking exactly the same. And on the left-hand side, it starts outside of its stationary distribution. So the left-hand process is moving very, very slowly towards its stationary, while the right-hand process moves very quickly. So you can actually tell the difference between the two processes. And likewise with the other examples here. In the rotational example, if you start outside the axis of rotation, then you can actually see it rotating, which helps you a lot with identifying. So we found, we can kind of complete this nice flowchart here, that we can have identifiability if and only if X naught is autorotationally invariant, and then we can potentially like estimate these parameters A and G transpose, which is what we want. But now we kind of have to go into, like in practice, how, we have some data where X naught is not autorotationally invariant. How do we actually estimate these parameters in practice? So the previous papers that try to estimate parameters from marginals never had this identifiability condition, so we introduced that to the literature. But because of that, because they thought that it's hopeless and we can't actually identify these parameters, they have really, really strict assumptions on these parameters. So for one, they assume that the diffusion is isotropic, so H is just a constant sigma squared times the identity matrix. And they also assume that they know sigma squared. So straight off the bat, they assume that half of their parameters are known before they even start. And they also assume some form on the drift such that it's kind of irrotational, so you don't get that crazy rotation examples that I showed. But we really think that these assumptions are unrealistic. I mean, you really don't know the scale of your noise before you start modeling, and you can also have these unobserved confounders, so these unobserved variables causing two or more of your variables in your system, and that case isn't covered by this isotropic case. So these unobserved confounders would appear on the off-diagonal entries of this H matrix. So the first thing, most people do when they're trying to estimate parameters is to kind of calculate the MLE. So we derive the MLE for A and H given these kind of marginal snapshots. But unfortunately, these marginal snapshots aren't enough. Like you have to have, there's these delta xi terms in the maximum likelihood estimator of A and H. So you have to somehow connect different marginal or different points within a marginal, different points within two consecutive marginals together to calculate this delta x. And we don't have that in our raw data. So we somehow have to figure out a way to make these connections from one marginal to another by connecting these simulated particles. And also, I'd just like to note that in the maximum likelihood estimator of H, we have this A term. So we actually have to estimate A hat before we even start to estimate H. So this problem of kind of determining what these delta x's are is basically called trajectory inference. So we start with these marginal observations in time in the middle here. And we want, and this comes from this kind of ground truth time series process, but we don't observe that. So we want to actually reconstruct this, what's called law and paths, to actually make these connections and make these trajectories from the marginal observations. And this is required for parameter estimation, as I just said, but it's also useful in its own right. You might want to understand the fate of a particular particle or kind of the fate of a particular cell into different kind of cell types. So this is almost always, this problem of trajectory inference is almost always kind of solved via what's called entropic optimal transport, EOT. So this optimal transport literature was really started with the problem of trying to optimally remove piles of sand from one location to another. I don't know, it's some weird kind of wartime mathematics thing that was going on. And we have this kind of given cost function. So uh, this is mainly for just regular optimal transport, but for entropic optimal transport, we're also adding this kind of uh, entropy regularization term. So with regularization term epsilon squared plus some cost matrix, and we want to.
Actually, was het van de koptelefoon of niet? Okay.
Sorry, Stephen, I couldn't hear you. Stephen, are you there?
Oh, sorry, I didn't realize I wasn't muted.
Oh, okay, no problem. So the goal of this entropic optimal transport optimization problem is to find this pi star, which is basically the probability that you go. It's kind of this joint probability that describes how you move from one particle at time 0 to another particle at time delta t. And you have this for every possible kind of matching, basically. You have this probability of going from one to the other. So basically, you're trying to, yeah, I mean, it turns out that this epsilon squared thing is kind of related to this Gibbs transition kernel. So this KXY thing, which we call the reference measure, is basically proportional to this basically this part of the probability density of the normal distribution. So people in the past have always selected this epsilon squared thing to basically be the variance of your SDE process. Yeah, this is kind of what I explained already. So they have this epsilon squared thing being equal to the sigma squared dt, where this, again, the sigma squared comes from where they assume that this diffusion term is given by this isotropic matrix, sigma squared times the identity. But we kind of want to generalize this. So we don't want to assume that H is like isotropic, or we don't want to assume that we know anything about A or whatever. So we were able to kind of generalize this reference measure to be actually proportional to this multivariate Gaussian density. So in this case, we can actually make a reference measure anything we want in the linear additive noise setting, and this turns out to be really, really useful when we're doing our optimization. And this is called generalized entropic optimal transport. So our estimation method, our overall algorithm for estimating these parameters is called GIMPy. And the first step, again, is to do this generalized entropic optimal transport. And this gives us these matchings between particles in time. And once we have that, we can kind of form these trajectories and then from there estimate A and H. So this, it turns out that this optimal transport problem is kind of minimizing this KL divergence between your reference measure. I called this KXY before, but now it's in the form of P of A K minus 1 and H K minus 1. And then in the infinite data limit, The MLE is also basically minimizing this scale divergence between your kind of trajectories that you formed and the possible kind of A parameters. So we can do steps 27, 28, 29, and then 27, 28, 29 over and over again in an iterative way. And this actually turns out to really help the estimation of A. So in the beginning, we kind of start, in the beginning of our algorithm, we start with this initial guess of A and H. And it can be anything you want. And as we go through each iteration of our algorithm, the couplings or the trajectories that we're forming get better and better, and also the parameters, drift and diffusion, get better and better. And hopefully we kind of converge eventually to something really good. And then at the end, we kind of can use these parameters to get our causal graph. So kind of on to the experiments now. So in our experiments, we give kind of 20 marginals. So we have snapshots of these marginal distributions at 20 different time points. And each marginal contains 500 observations. And the marginals are kind of evenly spaced with dt equals 0.05. And we're running 30 iterations of our algorithm. Where we start off, our initial guess is kind of A equals 0, and H is proportional to this identity matrix. And it turns out that our first iteration of our algorithm is actually exactly the same as what's called this Watt method, Waddington optimal transport, which is kind of the most popular method in the literature right now. Yeah, so we are, in these simulations, we're just totally randomly simulating like n-dimensional linear additive noise stochastic processes, and we're trying to estimate both A and G transpose. And you can see our method Gimpy does quite well even in high dimensions, dimension 10, and Watt, the previous method, kind of fails, especially for this GG transpose estimation for higher dimensions, while we are really, really good. This is by mean absolute error, by the way, so lower is better. And we also measured the correlation between the ground truth parameters and our estimates of the parameters. And we can see here that Gimpy does really, really well in the correlation of 0.98, even in the 10-dimensional setting, and also extremely well in when we're trying to estimate GG transpose. And this kind of shows you, on the x-axis, we have number of iterations, and y-axis is correlation. And then we have experiments for the dimension is equal to 3 and dimension equals 10. And we can see that our estimates of A and H are kind of slowly getting better as the iterations go on. It seems to kind of converge around like iteration 15 or something. So now a bit of a segue. So Vince and I, who's here also, are kind of really interested in causality. So we want to make this connection to causal graph discovery as well. So it turns out that given our like estimates of our drift BXT or A and our diffusion G, H, G transpose, we can basically get the entire causal graph. So the directed edges from I to J in the true causal graph are given basically by the variables that exist in some non-zero capacity within the drift. And the kind of multi-directed edges which represent kind of latent confounders or unobserved variables that are causing more than one of your features, are given by the off-diagonal entries in H, which is what we have as well. So we can kind of use this to run some simulations, and we can see in 3D, the true causal graph is this kind of collider graph, and Gimpy can perfectly estimate this, while Watt kind of fails in one case. When we bump this up to like 5-dimensional process, Gimpy still does perfectly. And again, this is in the no latent confounders case, so we'll get to the unobserved confounders later. And then this is in the 10-dimensional case. Gimpy again does perfect, while Watt completely fails, like overly estimates the number of connections. And then what I personally think is the coolest part is we can actually detect when we have these unobserved confounders causing 2 or more of your variables. So in this 3-variable case, we have the true causal graph with 1 latent confounder, and Gimpy can perfectly find this latent confounder and see that it's causing both 2 and 1. In the 5-variable case, we have 3 latent confounders, and Gimpy also detects all of them. But it does add this spurious kind of green edge here from 5 to 3. But otherwise, it's really, really good. And this is kind of our aggregate results for causal discovery. In the top table, we have kind of the Hamming distance. So you basically get a score of 1 if you put in an edge to the causal graph that shouldn't be there, or took out a causal edge that should be there. And this basically lowers better. So Gimpy always does better than this previous method in all dimensions. And then we also have it for these simple directed edges, which Gimpy always does better, and these kind of latent V structures where Gimpy always does really well too. So yeah, I'm really excited about this paper. So any questions from any of you?
You said you had a preprint available, right? Or that's coming?
Yeah, it's coming. So
Okay.
it'll be available I'm hoping in 2 weeks, but maybe more realistically sometime in November.
Yeah, no worries. But please share it. Just
Yeah,
remind me, because I'm
definitely.
definitely going to need to digest this. And these aren't very insightful questions, but please humor me. So remind me that application that with tracking genes.
Yeah, so the main application that's in the literature at the moment is this gene regulatory network. So I guess kind of you have these stem cells that start off at a particular gene expression, and then they kind of divide into different types, and then their kind of gene expressions change. And then, yeah, I guess that's a stochastic process. I don't really know anything about it, but the contaminant transport one is kind of more interesting to me. I've seen a couple papers, even like Keith Bevan has done a couple papers on it, where we have kind of these contaminant plumes or tracers that are kind of moving through groundwater, and we want to understand kind of the stochastic process that drives each individual contaminant particle. And these kind of the advection will kind of tell you the direction of groundwater flow, and also it'll tell you a bit about the hydraulic conductivity, maybe, just because of Darcy's law. And then the diffusion will kind of tell you maybe some other properties about the system, like the properties of the soil or geology, and also the, what do you call it? The kind of, maybe it's a Peclet number, but it's kind of how chaotic the particles are and how they're diffusing out. So
Yeah, it's interesting. I hadn't seen the gene regulatory networks example. I was just going to note that, recently I've seen in statistical departments, and they tend to be working on like neuroscience problems, like developing the brain is a high dimensional space that we can only, it's a dynamic system and we can only observe it indirectly. And these people are working on techniques for like monitoring the brain. But it's very interesting because it's a general problem. The Earth system is a high dimensional dynamical system, right? So that's cool to see.
yeah, I mean, maybe one of the nice parts about this earth science or groundwater application compared to genes or the brain is that actually it's not high dimensional. So this is just like a contaminant plume going like expanding in three-dimensional space. So you can actually, sample a lot of data potentially, and you don't have to worry about cursive dimensionality stuff going on. But yeah, in the brain, yeah, I'm wondering, like, there could be applications where you have kind of a coarse measurement of what's going on in the brain. You can't track individual neuron firings. You kind of
Exactly, right.
wanna,
They're using MRIs, and they're able to, what they're detecting is like a blood flow signature, which is lagged. And anyway,
yeah.
so just there are a lot of analogs. Another boring question I had, just when you report your metrics on Gimpy versus Watt, first round, you report mean squared error.
Mean absolute error. But yeah.
Mean absolute error. Yeah, this page. So for the G transpose,
yeah,
those are squared units essentially.
Yeah, in a way they are, yeah.
Okay. Again, this is not the point of your paper, so I feel a little bad.
No, it's an
Pointing at it,
important
but-
point because you actually you can never kind of estimate G just because of the properties of, I think, normal distributions and maybe other distributions, but yeah, like G is
that's a Cholesky decomposition.
Kind of, yeah, but it's more of I don't know. It's more of just the like a covariance matrix versus some other thing that's going on which you can't detect.
Okay. Well, yeah, happy to take your word for it. Okay, thank you.
Yeah, no problem.
Joe, somewhere in your derivation, you mentioned KL divergence. Are you actually using KL divergence, or I'm just curious because there are a lot of reports that optimization using KL divergence is not terribly, a lot of people have trouble with it. So,
yeah, that's a good question. I mean, even one of our co-authors was confused about this point as well. So, yeah, okay, so we have this outline of what Gimpy is doing, but in fact, we never actually compute what the KL divergence is.
okay.
So in step 27, we're just applying this Sinkhorn algorithm, which just is basically a bunch of matrix vector products. We never, there's no KL. But it turns out that it's actually minimizing the KL between this kind of reference measure and the kind of transitions that you're trying to estimate. And then for the step 28 and 29, we're just doing the maximum likelihood estimation, which in the case of linear additive noise models is just closed form. So we never actually compute the KL here either. But in the infinite data limit, it is also minimizing the KL. I think the main reason why we are putting it in this KL space is basically just it helps us with some of the theory eventually. So for example, in the infinite data setting, we have that at each iteration, the KL is either kind of decreasing or staying the same, which is nice.
Yeah.
Yeah, so you couldn't do that really without the KL.
Yeah, I mean, I was just curious because particularly in Gaussians, you can minimize KL divergence without ever using KL divergence.
Yeah.
You just have to make the means and covariances match up, and you're done. You can always compute KL divergence, but you don't have to use it as a metric. Yeah, that's just curious how you were doing it. Yeah.
Yeah, we've been thinking of actually trying to compute KL divergence, but we haven't done it just to kind of check this kind of decreasing plane. But yeah.
Well, Manuel has a code that'll give you a KNN based. Manuel, am I correct, Manuel? You have a code that'll do DKL?
Yes, it does scale divergence using inverse neighbors.
In high dimensional spaces, right?
In high dimensional spaces, yes.
Okay.
And maybe you can send that in the chat. I can take a look.
Hey, Joe.
Yeah. Hi, Jasper.
I missed a large part of your talk because I had to teach and there's an exam today. So students, they actually ask questions today, which is a good start, undergrad. So, but first of all, I thought it was a really wonderful talk. Obviously, a lot of mathematics, which I very much appreciate. But I had one question. I think it's on an earlier slide. You discuss where you mentioned something to the effect of that the sigma square. So you use sigma square times an identity matrix, and you said that sigma squared is hard to determine a priori. So in theory, I would say that the sigma square should be related to your measurement uncertainty, right?
Yeah, this is kind of a weird thing in stochastic processes. I mean, you're probably know a lot about this, but to me, like this diffusion is not really measurement uncertainty. Like I know I've seen like SDE papers that have like a separate term or something for measurement uncertainty, but I don't know. Like this is more like a inherent randomness in the process itself.
Okay.
But maybe it can also cover observational errors as well. I'm not really sure.
I think it's because in that case, usually because the sigma square usually, I mean, if it's measurement uncertainty alone, then we have information about devices, we can get an estimate, but usually that's a lower bound because when we apply all this theory, that sigma square also includes everything we ignored essentially in our model. So
yeah,
anyway.
that is the case in most statistical models, but in this case, like Brownian motion is literally like, random air particles bumping into each other and with dust particles or whatever, and that actually forms kind of this random aggregate kind of movement where
Okay.
it's not just observational error, but I think Vince had something to say about it. He's the first author of this paper, so.
I guess as I understand it, I've seen before that the diffusion is seen as driving noise. In the case here with classical stochastic differential equation, it's modeled by Brownian motion. So your driving noise is adding like a normal noise at every time increment. So that's like from the inherent from the process itself, maybe from, for example, unobserved confounders, maybe from inherent randomness of the system. But then measurement noise is a separate thing. It's like every time you take a measurement, like an observation, whether like a trajectory or a snapshot, you just incur a penalty like from some other distribution. So I've seen people use both notions of noise and they are separate, I think.
Okay, so so two things, I don't know if they're relevant, but so the sigma squared, that reminds me a lot in the Kalman filter, right? Where you add model error to your state forecast, right? Or that produces your state forecast so that you can then get your analysis state. And the second thing is, I think a lot of what is presented here, you can use this also for Markov chains, right? To let them move through a state space. So with the Hamiltonian and all that, it's very close related. I don't know if that's been explored before.
Yeah, we actually presented this to a mathematical audience yesterday, and yeah, someone suggested looking into kind of hidden Markov models. So yeah, there's definitely a connection there.
Yeah. Nice. Yeah, sorry, I got too late, so I didn't really follow I got in late in the talk, but thank you so much. Wonderful.
Sina?
Great talk, Joseph. So I was wondering if you could show the slide for the performance comparison. So I think I missed something. How was the coefficient benchmarks derived or calculated that you basically compared these two methods with each other? Like the how are these metrics calculated based on what benchmark?
Well, it's not really like a known benchmark. We just literally totally randomly generated an A and GG transpose and then sampled, marginal observations from that process and then tried to recover those parameters.
So my question is were those like A and G, like basically the Cholesky decomposition, which is, I think that's my understanding of GGT, is were there like isotropic or were they not?
No. So there's no restriction on A or GGT. We just did whatever. I mean, that's the main point of the paper actually, because everyone else has assumed that A has a certain form and also GGT is isotropic, but we're like the first paper to actually move away from that.
Yeah.
And we're showing that we can
so
recover arbitrary linear additive noise models.
So yeah, that brings me to a question that if like when you sampled from A and GGT and they were not isotropic, and your method can care for isotropic estimation, which is basically the novelty, definitely your performance would be better compared to WOT, which doesn't care for that. Because if I have gotten that correctly, basically that would be like for the diagonal entries, that would be 0 in WOT, but your method will obtain something, and that will basically result that always your method would be better compared to WOT. Is that correct?
Yeah, that's true. There would be unfortunately, there would be no fair comparison in this setting to our method, just because we're the only people that do this. But I do take your point. It would be interesting to also add a table where the true kind of system is isotropic, and maybe Gimpy still does better than Watt just because of this iterative thing. And yeah, that'd be interesting to look at as well.
Oh yeah. Just one last question. Like, I know like it's absolutely out of scope of this paper and your research at this point. How much do you think your observations are dependent on like basically the linear drift and additive noise that you assumed and you basically worked upon that? Do you think that if you kind of basically go with the nonlinear method, the results would differ so much, or?
Yeah, so we know, like, even theoretically, we would be totally screwed with like multiplicative noise, some other noise, but maybe like non-Gaussian noise would still work. I'm not sure. Just like it has to be additive noise for sure. For the nonlinear drift, I think it can still work, but we haven't actually tested that yet. So
Awesome. Great work. Thank you so much.
yeah, thanks.
Joseph, great presentation. I have a question. So it seems that the GIMP algorithm is identifying correctly the directionality of the causal graphs, even
Sorry,
including
what of the causal graphs? Can you say that again?
the directionality,
Yeah.
right?
Yeah.
Because it's looking at the trajectories, so you're taking that into account to account for the directionality, right?
Yeah.
Even when you have latent confounders. So how can you physically describe, maybe testing with experiments, those latent confounders? Because
Like
I guess
what an example of a latent confounder in the real world would be, or
will
what do you
be,
mean exactly?
yeah.
Yeah. Yeah, to be honest, the causal graph stuff, I'm not sure. At the moment, at least, I'd love to find an application to hydrology, but I'm not sure the causal graph stuff is applicable to hydrology. But at least in the gene case, I could imagine, you know, you can have some gene that's unmeasured, right, that can cause two of your measured genes, right? And that would appear as a unobserved confounder.
I have a further question. So maybe eventually, can you use the same type of algorithm to account for the weights of the links?
Yeah, so actually, the weights of the links are basically just A and G transpose. So the kind of parameters are giving you the weights. And in fact, you can see like some of these arrows are red and the others are green. I think red means like a negative, like 5 is causing a decrease on 3. And then green is like a positive. So 5 is causing an increase in 9. So we are actually showing some sort of, well, sign weighting at least. But yeah, the parameters themselves are giving you the actual weights.
Okay, thank you. Great job. Thanks.
Yeah. And also, maybe I should have mentioned for Layla, people like are interested in causality. In this case, we can actually have some cycles. So we're not necessarily just detecting DAGs. We can have some cycles, and this is just a result of us looking at actual time series, right? So we can have some feedback loops in these time series.
Do you consider time series that are not complete?
No, we did not consider that.
Sorry, what do you mean by incomplete?
Having gaps. Usually when you go to the field and there are some issues with the instruments, you don't have like complete data sets in many hydrological or geophysical settings. So it's difficult to use sometimes machine learning approaches, or you end up like averaging to a certain time length because you don't have like time series completed at this certain time frequency.
Yeah.
Mhm.
One thing I'll say is that for these kind of marginal observations at different times, you actually don't need the same number of points at each
Mhm.
time. So like everyone in this literature basically assumes you have it, but it's actually like without loss of generality, you can kind of do the same thing, I think. So you can have different points at every time, and your times can actually be unequally spaced as well. It doesn't really affect much, but our code is kind of maybe a bit too restrictive at the moment. Maybe it wouldn't allow you, but it is definitely possible. Yeah.
This is great work. Thank you.
Yeah.
Any other question? Okay.
Jasper, I have
we are-
time afterwards if you want to like
Hmm.
if you want me to explain the beginning, but yeah, we can everyone else can leave if they want.
Actually, Joe, one other question
Yeah.
came to mind. Do you have any idea on how closely spaced in time your observations would need to be for your inference to become, to approach being perfect? Yeah.
Yeah, that's a really funny kind of question because it's, I don't know, stochastic processes are really weird. So it turns out that having finer grained observations are usually give you worse results. So there's kind of a happy medium, like you have to have more than two, like usually, but yeah, if you make dt like really, really small, like 1 to the -5 or something, then what happens basically is that your Kale divergence starts to kind of explode a bit because, again, we're the only people that assume like unknown diffusivity. And when you have diffusivity changing, then the KL kind of does some weird stuff. The main thing that's important is to have a really good estimate of the marginals at each time. So you want a lot of data points per marginal, but the time granularity is not really as important to keep track of.
So how would you get lots of observations? Just space?
Well, yeah, I mean, I think in hydrology it might actually be easy-ish. Like for contaminant plumes, you would maybe have I don't know. Well, at least in oceanography, when they're kind of looking at contaminant plumes, I know there's some kind of remote sensing based stuff that they can use where they can literally look at the distribution of this plume, right? And you can basically sample as many points as you want in that setting, I'd say. And also in the gene regulatory network setting, I think it's not a problem to have like lots of cells at each time point. So that's usually not a huge limitation. It might be for some applications, but yeah.
But in principle, if you had many, many observations at each time point, that would work. It's just that in groundwater, it's difficult to get those. Yeah.
Yeah.
Okay. Makes sense.
Yeah, it's a really good question. We had some interesting discussions yesterday. It's like on the one hand, if you only had, for example, 2 times and like they're kind of pretty far spaced, then like they could both be the same. Like you could have non-identifiability because like you could already transition, let's say, a stationary distribution. And as we saw, like the first example, you could have multiple systems have the same. So then, if just from those 2 observations, you can't do much. But then we found actually, so one thing that we use is we use entropic optimal transport, and something that's well known that was established, I think, around 5 years ago, were these bounds for this entropic OT problem. That which we use as a subproblem for our optimization. So if you look here, there's a regularization epsilon, and when you use finer and finer grained spacing and time, if you go to the next slide, Joe, that epsilon is exactly sigma squared dt. So you send dt down, you're sending epsilon down, and you need the number of observations you need to have some kind of good bounds. It scales, I can't remember what, but you need proportionally more observations, which is somewhat counterintuitive because it leads to, in this setting, it tells you that more data could be worse, but it's consistent with what people have found in the entropic OT community, that just the amount of data that you require given smaller and smaller regularization is just, it's very data hungry.
Any other questions?
Okay, I think with that, we want to thank Joe and Vincent for the great presentation today. So we are gonna actually release this presentation after they publish their preprint or their paper. So Joseph, please let me know when I can release this presentation. Yeah, and we're gonna see each other again in 3 weeks for Andrea Chavez's presentation. She is a PhD student at the University of Texas, El Paso, and she will be talking about geoscience and generative AI and large language models. So yeah, thank you everyone and have a great day.
All right. Thanks, guys.
Thanks, everyone.
Bye-bye.
Thank you.
Thank you.